Welcome back. So today we're going to talk about the end of chapter 9, which is all about relations and functions. So this first part of section 9.3 is on relations. And what a relation is well, the way your book is defining it is by a subset of the Cartesian product of two sets. So here we have we have two sets, A and B. And remember, when we take the Cartesian product, A cross B, that is the set of all ordered pairs A comma B, so that we take the first element is something in A, and the second element is something in B. And so I think we used this notation. I mean, we did not use this notation when we introduced sets, and I think we used it a little bit when we were talking about one-to-one correspondences. So one-to-one correspondences are a type of relation, and we'll talk about they're more specifically and even a type of function. But relations more generally are just a set of ordered pairs. So what I have drawn out here are a bunch of examples of relations, and but instead of using this Cartesian product illustration, I'm using what we call arrow diagrams. And so here, if I just look at this first picture, which I called little a here, so here's an example of a relation. My first set, it goes from what I'm calling set A, which consists of the numbers 1, 2, 3, 4, to the set B, which consists of the letters A, B, C, D. And basically it has a way of, it's taking a subset of the Cartesian product because it's just matching up elements of A with elements of B. So if I wanted to use that same Cartesian product notation, I would say the relation looks like 1 comma A to describe this arrow, and it maps 2 to C to describe that arrow, and it maps 3 to B to describe this arrow, and it maps the last 4 to D, which describes that arrow. And so you can see that is just a subset of the full Cartesian product, where the full Cartesian product would be 1 comma A, 1 comma B, 1 comma C, 1 comma D, also 2 comma A, 2 comma B, 2 comma C, 2 comma D, all the way through to get every single ordered pair. So this is a subset. Okay, so here's one example of a relation. B here is another example of a relation. Actually, both of these are examples of relations that are one-to-one correspondences. So you might have noticed that. So here, both the set A and the set B have the same number of elements, and we've mapped the set A to the set B in a nice one-to-one correspondence. So here we can see, oh, both of those are examples of relations. I can do the same thing here, and I get write this as a bunch of ordered pairs, just like I did with the last example. C, here is another example of a relation. It goes from a set A to a set B. It is a subset of the Cartesian product. This one is one that is not a one-to-one correspondence, though. So it is not a one-to-one correspondence, but it is a relation. So we know it's not one-to-one because each one of these elements gets mapped to A. And in a one-to-one correspondence, we could only have at most one element mapping to A. And example D here is another example of a relation. So everything that I've shown you so far is a relation. But again, example D is not a one-to-one correspondence for a few reasons. One reason that it's not a one-to-one correspondence is that 3 and 4 are not mapped to anything, and in a one-to-one correspondence, they should be. Another reason is that B has too many things mapped to it. And the third reason is that 1 and 2 are both going to too many things, okay? So C and D are examples of, these are both not one-to-one correspondences. But they are relations. So notice, and I think this came up before when we were talking about one-to-one correspondences, um, that both the sets A and B are in one-to-one correspondence with each other, right? I mean, nothing changed about the sets themselves, A or B, in any of these first four examples. But we have some examples of relations that are one-to-one correspondences and some that are not. So we would say A and B are in one-to-one correspondence with each other. However, C and D, these two little examples, do not illustrate that for us. They're giving us relations that are not one-to-one correspondence. Okay, so just to kind of suss out those small points, there's another type of relation that we can now talk about, and it's actually not too new, but we haven't really mentioned it before. We can talk about something being a relation on itself. So here, in this last example that I've labeled E, A is a relation on itself, or A has a relation on itself. So in other words, A is both the domain and the codomain, or it is where things are originating and where they end up, right? So here, this is an example of a relation, so I don't need necessarily two distinct sets in order to have a relation. I here am saying this still is a subset of the Cartesian product, but in this case, it's of A cross A. So here, my ordered pairs would look like, well, one of them says 7 goes to 1. Another one says 7 goes to 3. Okay, it's not going to be 1 to 1, but it is still a relation. Another one says 3 goes to itself, and also that 3 goes to 7. That's what this says. And the last arrow that I have here tells me that 8 goes to 8. Okay, so this is what we call a subset of the Cartesian product of A cross A. It doesn't need to be the full thing. Okay, so that's just an example of a relation on itself. Okay, so this is generally the idea of a relation is pretty broad. It includes one-to-one correspondences, but a relation doesn't need to necessarily be a one-to-one correspondence. But relations can have certain properties that are helpful to identify. And so when I talk about a relation, I sometimes use this notation. I might call that relation R. And so, for example, in this example E, I would say R goes from the set A to itself. That's what this notation is telling me. So let's say that we have a relation on just one set. Okay, so we're not going from A to B. We're just assuming it's going kind of like this last example to itself. One property that we can talk about that a relation may have is it may be reflexive, or it may not be. And we say a relation is reflexive if A comma A shows up as part of the relation for every element in my original set. So notice I actually saw that in my example E here. I saw that 8 comma 8 showed up when I wrote down the list of elements, right? And so did 3 comma 3. But 7 comma 7 never showed up anywhere, and 1 comma 1 never showed up anywhere. So this is not reflexive. So it has two elements that are mapped to itself, but not all of the elements are mapped to itself. And that's what it means for it to be reflexive, is that all of the elements are mapped to themselves. So here are two more examples that help us better understand it. So here, notice A gets mapped to itself, B gets mapped to itself, C gets mapped to itself, and D gets mapped to itself. There's some other mappings happening in this example, but every single element is paired with itself at some point. So this first picture is something that is reflexive. However, this second picture is something that is not reflexive, just like in our last example E above. So here A is mapped to itself, but neither B nor C are mapped to themselves. So this thing is not reflexive. Another property that we can talk about relations having is what we call the symmetric property. And the symmetric property is a little bit more complicated. It says that if we have a pair of elements, A comma B, that's in the relation, then if I switch the order to B comma A, that thing is also in the relation. So an example of that would be this first example that I've illustrated two different ways. I've written it one way as a set of ordered pairs or a subset of the Cartesian product, and the other way using an arrow diagram. So it's the same relation, just two different illustrations. In this first illustration, I see, well, 1 goes to 2, and I also have that thing reversed, right? 2 goes to 1. I also have 2 goes to 2, and of course, that reverses in here too, right? 2 goes to 2. So for every single element in my relation, the reverse pair is in there as well. So this thing is what we would call symmetric. Something that's not symmetric would be like my second example here. So I can see, for instance, that if I started listing my ordered pairs, I'm going to have 1 comma 2, and I'm going to have 2 comma 1 since this arrow goes both ways. I will also have 1 comma 3, but I will not have 3 comma 1 because the arrow doesn't go the other direction as well, right? And the last thing I'll have is I'll have 2 comma 3, but I won't have 3 comma 2. So for those two reasons, this thing is not symmetric. And one more example of symmetric relation, just to make sure this is clear. Here, this last example is something that would be symmetric, and you can visually see from these arrow diagrams if something is symmetric by just noting that all the arrows should go both ways. So notice they have kind of pointy parts on both sides, right? So if all the arrows go both directions, then you should be symmetric. So we don't need arrows going both directions between every single element. We just need every arrow that exists to go both directions, just like we had with number 1 here. And notice, I guess, visually to note on the reflexive property, we need every element to have a little, curvy arrow going back to itself for the reflexive property. Finally, one more property that we like to discuss, or we like to think about with relations, is again a bit more complicated, but we have touched on it before, and it's what we call the transitive property. So if this word sounds familiar, it came up when we were talking about inequalities. So the less than or equal to sign is an example of something, a relation that has the transitive property. And formally what the transitive property says, it says that if I have ordered pair A comma B in my relation, and I have B comma C in my relation, then I also have A comma C in my relation. The other way like I said, we've described this transitive property as using inequalities. So if 1 is less than 2 and 2 is less than 3, then sure, of course, 1 is also less than 3. An example of a relation that's not transitive that we've already mentioned is something like I am is like motherhood or something, right? Like I am the mother of my son, or maybe I am the mother of my daughter, and my daughter might be the mother of her child. That does not mean I am the mother of her child, right? I am the grandmother of her child. So it's really easy to make these with familial relations. However, if I said I'm the relative of my daughter, and my daughter is the relative of her child, then I am also the relative of her child, right? So so familial relations work both ways. More formally, these examples, so example 2 here, using an arrow diagram, basically what we want to see is that it's a little bit harder to test because there are a lot of cases, but we want to look at, let's see, I can go from A to B, and I can go from B to C, and yes, there is a way for me to go from A to C. Okay. I can go from, yeah, there's all sorts of ways that this one works out nicely. Yeah, so that's the main thing. So let's see. Here's an example of, I think it's maybe more helpful to look at this example of one that's not transitive. So this example is not transitive. Let's see. Parts of it are like appear to be transitive, right? I can go from T to R and R to S, and I can go from T to S, so that seems to be transitive. But one thing we don't have that we would need, in fact, I think the only thing we would need, is I should be able to go from R to U. So notice I can go from R to S, and I can go from S to U, but I don't have any pair R, U. Okay. An equivalence relation is a relation, so any kind of set of ordered pairs that has all three of these properties. So it's reflexive, it's symmetric, and it's transitive. So here's an example of something that's a equivalence relation. So let's say I have this set A is the numbers 1 through 40, the integers 1 through 40. And I'm going to call my relation R that to mean has the same ones digit. Okay, and so then what that means is things that are in this relation are things like 1, 11. They have the same ones digit. So does 1, 21. And so does 1, 31. Right? But 41's not in there, so not that guy. Another example would be like 2, 12 is in that relation, and 2, 22 is in that relation, and so on, right? We can keep kind of going through this pattern. But notice things that aren't in there are things like 2, 20, right? So they have the ones digit of 2 matches the tens digit of 20, but not the ones digit, right? So that's not in my relation, okay? So this is an example of something that is reflexive because basically it doesn't matter what order I match these two things in. If one has the same 11, ones digit as 11, 11 comma 1 is also going to be in there. So it's reflexive. Oh, I'm sorry. Reflexive means that 1 has the same ones digit as 1, so 1 comma 1 will be in there. Sure. Symmetric means that 11 comma 1 will also be in there. The order doesn't really matter here. And it's also transitive because if 1 comma 11 is there and 11 comma 21 is in there, which it should be, then 1 comma 21 will be in there. Okay. So this satisfies all three of those properties. And the reason why we care about equivalence relations is that they partition a set into disjoint subsets. So if I think of all of the stuff that could be paired with 1, that's like 1, 11, 21, and 31. And all of the stuff that will be paired with 2, that's like 2, 12, 22, and 32. And I can do this with all of my digits, including 10, 20, 30, and 40. And if I do this, all of these little subsets are going to be disjoint, meaning they don't have any common elements. So it's my way of partitioning a set. Okay, so our reason for really talking about partitions is they're a more general notion. They give us some kind of characteristics and some ways of talking about setting up the notion of a function. And a function is a type of relation, but it has some more, it has a more specific quality that it needs to satisfy. So a function is a relation, and but more specifically, it matches each element of the first set to exactly one element of the second set. So let's look back at our original examples of relations here. So we said all of these examples, A, B, C, D, and E, are all examples of relations. However, they're not all going to be examples of functions, okay? So A, that is an example of a function. Every single element in the first set is mapped to exactly one element in the second set. Same thing with B. Every single element in the first set is mapped to exactly one element in the second set. So these are also both functions. Okay, so A and B are both functions. But C is not going to be a function. And the reason is that, oh wait, shoot, let me see here. I'm sorry, C is also going to be a function in this case, right? So C is a relation, it is also a function. So every single element in the first set, so 1 is mapped to exactly one element, 2 is mapped to exactly one element, 3 is mapped to exactly 1, and 4 is mapped to exactly 1. So we have all the elements that are in here are mapped to exactly one element. So yep, this is also a function and a relation. Oops. But D is where we have an issue. And that is because 1 is mapped to not exactly one element in set B, it's mapped to 2, right? It goes to both A, little a, and little b. And 2 goes to 3 different things. It goes to B, C, and D. So here, D, this is not a function. And similarly with E, we can still talk about functions on themselves, but this is not an example of one because, for instance, the element 3, well, it goes to both 3 and to 7. So for that reason, this is not a function as well. Great. So let's see, I think I wrote these here. In the example, A, B, and C are functions, but not D and E. Okay, so let's look at some different examples of functions that we've already kind of seen throughout the course and that we often see just kind of popping up. The first major example that we see is sequences. Sequences are examples of functions. When I think of a sequence, I'm thinking of just like a list of numbers where I care about that order. And so, for instance, 2, 4, 6, 8, 10, the sequence of even numbers here, this thing is a function. And the way I want to think about there being an ordered pair, because right now it looks like just a list of numbers, is I want to map the, so if I list out this list, 2, 4, 6, 8, and so on, the thing that each number is mapped from is the order term in which it appears. So we'd say the first element goes to 2, is 2. The second element is 4. The third element is 6. And the fourth element is 8. The fifth element is 10, and so on. So in this way, we can kind of think of this as a function, which is, again, of course, a type of relation. And so all sequences are going to be functions, because if I'm looking at the first term, it should only go one place, or the second term in the sequence, it should only go one place. Some specific examples of types of functions. We have two main types of sequences. We have two main types of sequences that we talk about in this section. We have an arithmetic sequence, and we have a geometric sequence. And the difference is basically in how they grow. So in an arithmetic sequence, we start off with what we'll call A is our initial term. And to get the second term in the sequence, I'm going to add some value D that I call my common difference. And so notice, each time I go up to the next term, I'm just adding another, I'm adding D one more time. So this is, we go from A to A plus D to A plus 2D, 3D, 4D, and so on. And so this last, or this, it's not our last guy, but some generic term in the middle, what we often call the nth term, looks like A plus n minus 1 times D, right? Because my second term was just 1 times D, my third term was 2 times D, my fourth term was 3 times D, and so on. So generalizing that, my nth term should be A times n minus 1 times D. Or yeah, A plus n minus 1 times D. Okay, so looking at an example, here we can see, so if we look at this example 7, 11, 15, 19, 23, I notice that in order to get to each term, I'm going to add 4 every time. And so that is going to be my common difference, D. So my initial term is obviously going to be 7. That's the place I start. And then what I do is I add D equals 4 every time I want to get a new term, right? So in other words, my nth term would be, or my nth term should be 7 plus n minus 1 times 4. Or if I wanted to find specifically the 10th term in my sequence, it would be 7 times 9 minus 1, or plus 9 minus 1 times 4. Oops, 10 minus 1. Sorry about that. I already did the minus 1 in my head. And that should give us 43. So I already know, so using this form, I know what any term in my sequence is without actually having to list out the previous 9 terms. Okay, so that's what we call an arithmetic sequence. So what makes something an arithmetic sequence is it's increasing by adding some constant integer value here, like we added 4. So this plus 4 every time is what is making this a arithmetic sequence. A geometric sequence, we are, instead of adding some integer, we're going to multiply by some integer every time. So again, we'll start off with this number that we call our initial term. I wonder if you can hear my dog snoring in the background. She's so bored, apparently. And then every time I want to look at a new term in the sequence, I multiply by some number r, which I call my common ratio. And again, a generic term in this sequence, or the nth term, looks like a times r to the n minus 1, right? Because my first term has no r's that I'm multiplying by, then I take a. The second term is times 1 of the r's, the third term is times 2 r's, the fourth term is times 3 r's, and so on, so that the nth term will have n minus 1 r factors in there. So looking at an explicit example here, like 5, 10, 20, 40, 80, here, if I look at this, I see that in order to get from one term to the next, what I have to do each time is multiply by 2. So I'm not adding a constant value. I'm multiplying a constant value. So I multiply 5 by 2 to get 10. I multiply 10 by 2 to get 20. And then I multiply 20 by 2 to get 40, and 40 by 2 to get 80, and so on. Okay. So in this example then, my initial term, of course, is just 5. And my common ratio that I'm multiplying by is 2. If I want to find the nth term, so some generic term in the sequence, that would be 5 times 2 to the n minus 1. So the 10th term, specifically, I could ask for any term, but if I wanted to find the 10th term, that would be 5 times 2 to the 10 minus 1, or 5 times 2 to the 9th, which should be 2048, or 2048. Great. So those are two different types of sequences. A couple other type of sequences that we can see. I guess your book doesn't call them explicitly sequences, but definitely that's kind of how we have encountered these things before. So one example that we've already seen is, and I think some of the exercises, is the rectangular numbers. So the rectangular numbers we can think of as this list or sequence of numbers, 2, 6, 12, 20, and so on. So notice the pattern in this list on the right is not achieved by adding some common difference or multiplying by some common ratio, right? Because to get from 2 to 3, I could think, well, I add 4, but that doesn't work to get me to 12. Or I could go from 2 to 6, I could add, or I could multiply by 3, but that again won't get me to 12. So we've seen a sequence that comes up in thinking of these as rectangular numbers, where the first term, I take 1 times 2 to get 2. So these numbers are numbers that can be represented in arrays where the 2 dots on the shorter side is 1 less than the dot on the larger side. So the second term would go to 2 times 3, the third term would go to 3 times 4, and so on. So that the nth term would go to n times n plus 1. Okay, so here's an example of a sequence, and we can think of it as a function by just assigning, by considering the ordering and assigning the integer to each term in the sequence. A similar thing can be done with exponential growth. And so we haven't really talked about exponential growth in this course, but I do want to talk about it a little bit because it is coming up a lot more in the media. So one example of exponential growth that your book talks about is amoebas. So amoebas propagate by basically just splitting in two. So, oh goodness, there's a name for this, and I should have looked it up, but it's in your book. But they don't need to mate in order to make a new amoeba, they just split. So you start off with one amoeba, and it splits into 2 amoebas. Each of those amoebas can split into another 2 amoebas, so that at the first splitting you have 2 things, and then at the second splitting you have 4 things, 4 amoebas. And then each of those guys can, of course, split into 2 more amoebas, right? And we should have 8 things at that point, 8 little amoebas, and so on, right? So this is an example of exponential growth. And again, just assigning and ordering to this exponential growth is what gives us a function. Where you might have seen this very similar diagram, or the word exponential growth more recently, is with an explanation of COVID-19. So I'll probably talk about this more at some point, but specifications of this. But here's a great place where, at very minimum, if you're looking in the media and you see some articles about exponential growth, and you want to do a quick little explanation as to how exponential growth is talked about in the article, or what it means in order, or with relation to this virus and what's currently going on, that would be a great way to get participation. I'm going to try to think of a way to write this up as an extra credit opportunity at some point. Okay, so great. So those are some examples. To finish off this section, we have a few different ways of talking about functions. So I just want to talk about different representations and, of course, the function notation. So the function notation we use is we say a function f goes from a set A to B. So we use like this kind of notation to denote the function going from A to B. So if A is an element of the what we call the domain, so here big A is the domain, and big B is what we call the codomain. And let's say that A is some element in my domain. Then where it should map via the function is to some point f of A. And we say it does that through the function. Okay, so f of A is some element in B that is mapped to by from A by f. Okay, great. So using this example or this notation, we can look at some of those examples above and write them using function notation. So I think we talked about the sequence of even numbers, and it says that if you take an even number n and you take, or sorry, if you take a number n, like an integer, and you want to identify the even number associated with it, you just multiply by 2. So the first even number is 2, the second even number is 4, the third even number is 6, and so on. Okay, so it's giving us that mapping. For the rectangular numbers, we would say f of n is n times n plus 1, kind of using the same map we were talking about up here. So that's how I use function notation to write that same map. For cubes, I would say f of n is equal to n cubed. And for the amoebas example, I would say f of n equals 2 to the n. That's how I would write this. So you can see this through our example here. This is just 2 to the 1. This is 2 squared, 2 cubed, and 2 to the 4th, and so on. So we're just multiplying by another factor of 2. Okay. So this is our function notation that we would use to talk about functions. So it just gives us, it's just a notation that is handy that we can sometimes use to discuss functions. However, functions can have all sorts of different representations. So it's really important when thinking about functions to really be able to interchange between each of these different representations. And your book mentions that when introducing functions, it's really helpful to introduce a function using multiple different forms. So for instance, we can talk about a function as using arrow diagrams like we did a lot at the beginning here. We can also use a table, which was very similar to how we did with some of those lists. So this is like our set of ordered pairs. So these both are two different representations of exactly the same function here. Another way we can represent functions is with machines. The nice thing about representing a function with using a machine is that it's a really dynamic way about thinking of a function. And so using ordered pairs, which we've talked about, and even tables are really static like visualizations of a function. They seem to really they don't really illustrate as much kind of something happening to um, the elements in the domain to get the elements in the codomain, which in some ways can be helpful. Sometimes it doesn't feel, sometimes certain functions don't really have that dynamic relationship. But with a function machine, we get this really dynamic demonstration of a function. So this function machine tells me, hey, if I put in the number 3, well, I put it in the machine, and what the machine does is it squares that number. And so what it pops out is 9. Okay, so it gives me kind of an action as opposed to something, like I said, static. Again, a list of ordered pairs is really similar to a table. It's just maybe a more horizontal list. In a graph, we can be graphing these ordered pairs. So here we call this x-axis, usually the domain, and the y-axis here, the codomain. And so I think we saw this visualization. This is like what we call the Cartesian coordinates, because it's a way of assigning a Cartesian plane. I'm sorry, because it's a way of forming a plane using these Cartesian coordinates, right? So that each one of these dots is the point A, comma B. Of course, formulas we can think of as being a representation of functions. So for instance, the area for a circle, pi r squared, we can think of the area for a circle really kind of as changing as we change the radius of that circle. So as the radius of a circle expands, so does its area. And lastly, we'll talk about this more when we introduce geometry in chapter 12, but we can think about geometric transformations as ways to represent functions. Okay, great. So I have some starred exercises here that you might want to look at with reference to functions. Let's see. One of them is talking about sequence, number 29. Yeah, they're just nice. Actually, 29 and 31 are talking about sequences, but those would be good to discuss in office hours if you would like for participation points. Okay, I will.